you want to, I would say let's wait for the solutions for that. And if you still have doubts, maybe come to the office hours. I think that would be better.
Okay.
Because they have a certain way that they're gonna present that.
Like office hours on Monday,
Sorry?
like on Monday, or?
Yeah, or I think they should post the homework today, the solutions today. If it's still not clear, send me an email, we can set up a Zoom call.
Okay.
Sounds good? Yes.
Is there like any specific topics that you think we should focus on for review and studying? In particular, I guess?
I mean, you're basically asking me what topics are
Oh,
gonna
wait, yeah.
right? I mean, that's, yeah.
But is there anything that like stands out maybe?
That was a good try, but
Okay.
yeah,
Is there a higher focus on things after the first midterm?
no. There's no like it's not like if we've already tested you, whatever was covered before midterms, then you can ignore those things. That's not. It's you will be tested on the whole. Yes.
There's supposed to be tests about diffusion models. We learned those on Monday. What do you have like homework or?
So diffusion models once, can you read that?
Yeah, we learned them on Monday. We didn't have any like homework or like
Okay.
about it. So I was wondering if that was still something we could be like activities.
So it's not that the stuff that you've only gotten homeworks about are going to be on the exams. That's not
Mm.
the case. So it's the whole thing. Yeah. Yeah. I like how you're asking like the same question, but like in you know, yeah.
Mm.
Should we expect the exam to be at the same level of difficulty as the homework question?
I would say it will be about the same level of difficulty as the midterm, but longer. Maybe slightly harder because you have more time to finish it, right? Midterm was only about like I said, 45 minutes or something. So this is what, 2 hours, right? So it'll be longer, but similar like level of questions, similar style of questions.
So the difficulty will be similar to the midterm.
Yeah, maybe slightly harder. I would say maybe. I mean, this question is very subjective, right? So it's maybe it seems slightly harder to me, and it seems like it's actually easier for you. So, but we have tried to ensure that things are, you have proportional amount of time compared to the midterm. And multiple people, like the professors and like at least 2 TAs have gone through each exam and solved them by hand to ensure that and time themselves to ensure that it's doable by you in that allotted amount of time. Yes.
Since our midterm, or since our final,
Sorry, you'll have to speak up.
Since our final is a bit earlier in the week, do you think that there's gonna be a chance for a regrade request?
There's going to be chance for regrade request. Does that happen with the finals?
They've done it for like a few of my other classes. Like
Okay,
they did it with
I
CS 251.
my instinct is to say there's not gonna be, but I can double check and I can maybe send an announcement. Let me make a note of this. My gut instinct is to say no, but I'll just double check and get back to you. What was the other thing that I said I'll do? Oh, post the solutions, right? Post the practice exam. And then okay. Yes.
Repeat, are we expected to write like pseudo code or something?
If there is something, there might be like, write down what the algorithm looks like. Might be. Not actual like Python code or something, so we'll not be checking for syntax error and so not actual code, but there might be write down the steps. That's possible. Yes.
How good at calculus and linear algebra do you say do you need to be for the final?
Yeah, I saw the post on the XM also. It's what I had expected throughout the course and I would say midterm level. It's about the same. Yeah.
So, do you have any tips for, like,
The topics?
I remember in fourth homework we had a question on calculating gradients for back propagation for neural networks, but obviously it was a little bit more complicated than than scalar number case or like a basic derivative of a loss function with respect to a vector, because there were matrices involved, there were other vectors. So what sort of approach would you say we should take for something like that? Because I know personally that took me a lot of time to figure out, because we have to figure out which variables were influencing which and decide whether we need to sum over a couple of like multiples of
Right.
gradients and
So that's just practice, and also honestly, when we give homeworks, we have a little more flexibility in terms of how difficult can it be, because you have like sort of an open-ended amount of time, like 2 weeks or whatever, right? So and that's not unfair. I think if we give you slightly like arduous sort of
Yeah.
homeworks. I want to say exams are not gonna be like that. It might have questions related to that or a simpler version of it. And you might, depending on how familiar you are with the algorithm, you might still spend time on it if you are not very familiar with it. So familiarize with the process, like what is the exact algorithm, so that then the calculations become like a lot quicker. If you know what to do, it's gonna be quick. Right, but all those steps, I know the question that you're talking about, I think that was quite a lot, but then again, it was a homework question.
no,
Right, so,
I get that. It's just for that question, I knew specifically what gradients I needed to calculate for back propagation.
right,
It just took a lot of time because sometimes there was something like derivative of this variable with respect to a matrix.
Right.
And you have to.
right, you have to, keep track of that, yes. Yes, that you have to know, yeah. I'm not saying don't do that for the, like you can ignore that for the final, I'm not saying that. So that's something that you should know about. Yes.
Are we allowed to type up our cheat sheet, or does it have to be handwritten?
I don't think there was I think some of you did type during the midterm also. So unless did the TA send something? No, right? So the same rules apply. If you already did it for midterms, there's no need to change. Yeah. If you want to like go super small font and then bring a lens or something, that also works. Or you can do like this. I got these new glasses where like this bifocals, because my doctor said that I'm getting older, and so I have like myopic here and then the short-sightedness here and far-sightedness here. So you could get something like that. Anything else? Yeah.
In terms of conceptual stuff, could you go over VC dimensionality?
We can. So the idea of VC dimensionality is that, let's say, let's take a let's do it there. So let's first define a model class, right? So the model class is, let's say, we are living on a 1D, and my model class is that, let's say, So this is the x-axis. X like greater than t, it's positive, and x less than equal to t, it's negative. That's my only modeling class allow. So I can set a threshold, then everything towards the right is gonna be labeled as predicted as positive. Everything towards the left is gonna be predicted as negative, right? So now if I have a single data point here, can I perfectly, this is my training data, right? There's just a single data point, it's labeled as a class. Can you use a member of this modeling class and get 100% accuracy or 0% loss on this training data? You can, right? So you set a threshold over here, everything on this side is labeled positive, which means this data point is correctly classified, right? Now, what if it had label negative? Can you still perfectly classify this training data, which consists of only a single data point, using a member model of that modeling class? You still can. You just set a threshold over here, everything towards the left is negative, right? So that means this data point is correctly classified. That training data is fitted with 100% accuracy. Yes? So the VC dimension is at least 1. Because all possible labelings of data set of size 1 are perfectly fitted using a member of this modeling class. So the VC dimension of this modeling class is at least 1. Right? Now, let's say you have two data points. Yes? These are the labelings. Can you fit this training data using a member model of that modeling class? Yes. You set a threshold over here, everything towards the right is positive, everything towards the left is negative. It perfectly classifies the entire data set with 100% accuracy. Right? What if you had 2 pluses? You still can. What if you have 2 negatives? You still can. What if you have a negative here and positive here? Can you pick a model from that class to perfectly fit this training data? You cannot. Is there anyone who does not see why not? Everyone sees why not? Yes? So that's why the VC dimension is strictly less than 2. Because a data set of size 2 is not shattered by this modeling class, because we found a configuration which is not perfectly fitted by a member of this modeling class. So the VC dimension is less than 2, but we said it is greater than or equal to 1, so the VC dimension is 1. Yes? Let's change the modeling class slightly. Let's say that I can decide whether this is plus or minus. So I can set a threshold and it can be plus or minus, and this can be plus or minus. So I can set a threshold, and then everything, instead of everything towards the right being always labeled as positive, now I have expanded my modeling class to allow that I can flip the sides. So I can set a threshold and say that everything here is negative and everything here is positive, which was not allowed in my previous choice. Now, do you see that the VC dimension is 2? Because that one single configuration which was not being fitted by the previous modeling choice is now being fitted by this one perfectly with 100% accuracy. And it can be easy to show that the VC dimension is not 3, less than 3. You can easily find a configuration like this, for example. Right? So the VC dimension is saying is a proxy for how powerful your modeling class is. How complex a data set can that modeling class fit? Right? It's not doing parameter counting, because you see both of these models have the similar or same number of parameters. But clearly one of them is more powerful. So the power is defined by what is the largest number of data points which can be shattered, which means any possible Y configuration of access are perfectly classified using a member of that modeling class. So it's a proxy for how powerful that model is. It's a loose proxy, but it's still, like, you can still get meaningful bounds using this. Does that help? You see how it's a proxy for how powerful the modeling class is? Is there anything else? Yes.
Can you discuss the differences and similarities between the EM algorithm and k-means?
Right. Okay. So k-means is actually a special case of the EM algorithm. In the EM algorithm, could you describe what the EM algorithm does?
Doesn't it use Gaussian mixture models in order to classify different things into clusters?
Right. So what are the parameters? What are the sort of like hidden variables, and what are the parameters of the model that we need to learn about? So in mixture models, you have the means and the covariances of the Gaussians, right? And of course, you don't know the membership probabilities also, right? K-means is saying that we just do this clustering. If you, instead of having arbitrary covariance matrices, if you fix those covariance matrices to be spherical and of the same sigma, which means each cluster has sort of like the same sort of importance, and I think there's one more condition, then it basically simplifies to the k-means algorithm. So in when you're doing EM algorithm, you are evaluating mixtures, right? So maybe there is a cluster that's here that's like much bigger and has larger variance. There's a cluster here that has a smaller variance. The mixture model formulation will be able to fit this well. The k-means is saying implicitly that my covariances are spherical. So like these tilted or like, oval sort of like clusters are not allowed, right? Because the Euclidean distance is equivalent all around, right? So the covariances are only allowed to be spherical and they are equal for all the clusters, right? In that case, and you're not doing soft assignment, of course. Instead of doing soft assignment, you do hard assignments. So each data point, you don't say that it belongs to cluster 1 or Gaussian 1 with probability this and belongs to another one with probability this. So whatever is closest in terms of Euclidean distance, you assign to that cluster, right? So if you make these two changes, then the EM algorithm specializes to k-means. So the EM algorithm is a strict generalization of the k-means algorithm. You don't have to worry about optimizing for sigma, because if they are equal, it doesn't matter what it is. Does that help?
Yes. Also, just to follow up to that, this question was on homework 5, and we still haven't gotten a solution for that. Can we know when that's going to be out?
Yeah, I will also make a note of that. They should be out very soon.
Thank you.
If the solutions are not out by tonight, you should make some noise on Ed and then also email all the professors, like my exam is on Monday or like whenever, and solutions are not out, I have to study, and so let's start. Okay, yes.
Why are the eigenvectors of the covariance matrix the highest variance directions? For PCA.
Right. Why are
Because like wasn't it like you like eigenvalue decompose the covariance matrix? Like why does that work? Or like do we need to know the proof?
no, you don't need to know the proof. Why? That just follows from like linear algebra, right? I mean, that's why the definition of the largest eigenvector is the direction of the largest variance. That's just by definition, right? So given a data set, you build the covariant matrix, you find the top eigenvector, that direction is gonna be the one which has the largest weightage. Remember we did this construction where, I might have slides, where the data, actually, let me see. Does anyone remember what lecture number was that?
24.
It's not 24, it is 24. So you see this part here? You see this part here? So that is the spread. By definition, the first eigenvector is the direction of the largest variance. So you calculate the covariance matrix, you evaluate the first eigenvector, that is the direction of the largest variance. You're not okay. What is the confusion? Let's try to
I mean, like I get what you're telling me, but like it just feels like you're telling me that it's true, and like not like true. Like, do we have to know like the actual like intuition and like the proof behind everything?
I want to say yes, but I feel like that's not the answer you were looking for.
Yeah, well, like continue conversation. Like, because like what makes like the eigenvector special, like, and where does the variance come from?
Okay, let's step back, right? So a matrix in general is a linear operator, which means when you apply a matrix to a vector, it's gonna stretch, and it's gonna possibly stretch or shrink, and it's gonna rotate. Yes?
Yeah.
Okay, and let me repeat, because I'm not convinced yet that you are convinced. So, application of a matrix onto a vector can resize it and possibly rotate it. That's a linear operator, right? Eigenvectors are special directions where there is no,
Rotating.
right, so it's only stretching or shrinking, it's only resizing. The first eigenvector is the largest one because that is the direction in which the stretching is the most. That's the definition of the first eigenvector. So in that direction, why is that special? It's special because in that direction, if you have a vector and you multiply with a matrix, that vector is only gonna get resized. It's not gonna get rotated. That's why it's special. The first eigenvector is the one where the stretching happens the most, or the squishing happens the least.
Right. Yeah.
So that's why it's special. So that's the definition of eigenvector. The first eigenvector is the direction where there's no rotation, and the resizing effect is the largest. That can mean that it stretches the most or it squishes the least. Right?
Yeah.
So now, intuitively, if you are coming back to PCA, if these are the directions that are gonna stretch or squish the most, or squish the least or stretch the most, then effectively we are saying that when I multiply a vector with this matrix, most of the work of changing the input vector is done by these top eigenvectors. Let's simplify. Let's say there's only two eigenvectors, right? First one is larger, the second one is smaller. I'm asking you to do PCA and retain only one direction, right?
Yeah.
So if you only have to retain just one single direction, which one should you retain? should you retain the one where should you retain the direction in which the vector changes a lot, or the vector changes relatively smaller? Which one will lose lesser signal? That's the goal of PCA, right?
Yes.
Simplify the matrix in such a way that you minimize the signal lost. Right? Yes.
Could you just clarify what you meant by the larger?
Sorry?
Could you just clarify what you meant by the larger eigenvector? Is it the one with the larger eigenvalue associated with it, or what's?
Yes.
Okay.
Yes. The largest, the first eigenvector is the one which has the largest eigenvalue associated with it.
Okay.
Yes. Does that answer the question?
Kind of.
Okay. What is missing?
Like, then, are you okay? Yeah, so you have like this matrix, right? But then like, it's the covariance matrix. What about it being the covariances inside of there make it like so that like the projections and stuff work out?
So you have a covariance matrix and then the projections and stuff work out?
Yeah, like I get how the eigenvectors work, but then like, how does that translate to the first direction having the most variance, and also all of them being like perpendicular to each other?
Okay, so why are they perpendicular to each other, the eigenvectors?
Yeah.
Okay, so what you're saying is there might be directions which are not perpendicular to each other, and in those directions only stretching can happen and rotation cannot happen. That's what you're saying, right?
Sure. Yeah.
And okay, I'm claiming you can prove mathematically that cannot be the case. Eigenvectors have to be perpendicular. Eigenvectors are perpendicular. So for the purpose of this exam, I mean, you are welcome to think about this after the exam. But this is maybe like, I would say like second course on linear algebra or something where, so for now, you can just say that yes, the eigenvectors are independent. They are orthogonal.
Yeah, so like how much like black boxing can we like safely do on the exam? Like is it okay to like black box some of like the proofs and stuff and just like work with the algorithms, or is it better to like?
Could you give a concrete example?
The other one I'm like iffy on is the Ediboost exponential loss
Right.
proof.
Yes. So yes, that's something that I think you should know closely, and that's useful to know, and it's applicable in a bunch of other things that you may not realize now. So yes, please go through that. Yeah. So black boxing is what part is black boxing? What do you call black boxing?
Or I guess just like running the algorithms and like not really like proving them.
So I think you don't need to go beyond what is taught in the class and what was in the homeworks. I think a couple of times, did we do that in this course? No, we didn't. So whatever was covered in the class and what you did in the homeworks is pretty much the extent of what you should know, and you will be tested based on that. So we will not ask you to prove why eigenvectors are independent. And trust me, you sit down and you try to work it out, you'll be able to do it. It's not hard, but you know, that's not what we'll test you on. So we'll test you on, like, if there's an Ediboost question, it will be along the lines of what we did in the class. Right. So it's not gonna be harder than that, or go beyond that where we are expecting more. That was not covered in the class. I'm sorry, I still don't follow the black boxing part. Like, what did you mean?
No, I mean it's just like I feel like a lot of like the proofs for like the algorithms and such are like way beyond like the level of like difficulty of like everything else in the class, and I found them like very difficult to understand.
So AdaBoost is one of those
Yeah.
where it's harder than the rest of the class.
At least it felt like that.
Okay.
Or I mean, like I can like run the algorithm and that's fine. Like it's just like following.
Yeah,
the
that's not
instructions,
like
but,
again, that's not. I'm sorry, I'm interrupting, but we want our students to actually understand what's going on rather than, you know, like there should be a differentiator for people who are coming here and part of Purdue CS, and then people who are just running stuff and, you know, hate to bring this up again, but just using ChatGPT or just whatever, right? So we want you to be able to understand that. Is that what a lot of other people feel? AdaBoost was harder than the rest of the class? You feel that too? Okay, the proof of AdaBoost?
Yeah, I still don't fully get it. Like it just felt like a lot of like notation explosion and like.
Right,
not
so
a
it's,
lot
I
of-
understand, it's a lot of notation, like, and that part you have to, I mean, there's no way around it, you have to familiarize with the notation. But the simple idea is that in each iteration, one extra atom that you're adding, you are greedily minimizing the exponential loss. That's like the big picture idea, keep that in mind, and then everything else just, I understand there is a lot of notation. But once you familiarize with the notation and yeah, then it should click. Yeah, if like I would say maybe attend the office hours and like in person ask someone to go through that might help. Or maybe do you guys have study groups or COVID like sort of like dismantled all of that?
Well, what was like, you and Professor Zhang have office hours next week, like on the same times as in the Philippines.
Yes. Yeah, or the TAs, like they're being paid for this, so. I would say go, I also have study groups and talk amongst each other, that helps a lot, it did help me when I was in your position. Maybe, you know, you understood something that you did not and vice versa, and you can swap notes and discuss things, and it does help. Yeah, sorry, I keep getting.
No, it was all good. I kind of answered it. I just want to make sure, like, so we're proposing PCA like a two-dimensional graph, like, because we're getting, like, I mean, both examples I've seen of, like, we're grabbing both dimensions of the, or like both like variances. Is that really like the main business? PCA's like the main goal is like dimensionality reduction, right? So
Right.
if we're still grabbing like both dimensions, is that really like the main thing?
No, so in PCA, we don't grab all the dimensions. So we keep, like, if there are d total dimensions, we say we want to reduce the dimensionality to some k.
Okay.
K is less than d. And then you retain top k and you drop d minus k.
Okay.
Right, and that's the effective dimensionality reduction.
Okay.
So then everything lives in that k dimensional sort of subspace.
Okay.
Does it make sense?
Mhm.
Yeah. So which directions to draw? The ones which will have the least effect on, if that matrix is applied on a vector, how much does the vector change?
Mhm.
Right? So those directions are exactly the ones which will be like smaller eigenvectors and eigenvalues associated with those eigenvectors. So the smaller ones. So then you drop those, and that will have minimal impact or will have lesser impact than if you draw bigger eigenvectors and their corresponding eigenvalues.
Thank you.
Okay, anything else? So for the notation stuff, I would highly encourage, please get together, find a couple of friends. Just talk about, you know, what the notation is. AdaBoost, for example, maybe get together, few of you, on the board, one person write down what the notation is on the side. Right? Keep it on the side and then go through the proof and keep referring to the notation on the side. everybody has their own way of learning. That's how I learned this stuff. So that can help you, sort of like lighten the burden of memorizing the notation, because you know you have it on the side that is like ready to be referred any point you need it to be. So just write it on one side and then go through the proof, and then whenever like D or whatever notation comes up, just go. Does that help? But please have a group discussion about it. You still have some time. It will help a lot. Okay, is there anything else? Yes.
Just one final question for the actual exam itself, for the like finals, like, do we have assigned seats or anything like that? Is there anything specific that we should bring for the exam other than like the cheat sheet? Is there anything you would recommend, like?
No, I don't know about assigned seats, to be honest. I want to say no.
Okay.
Does that matter?
It doesn't, I know some classes, they like to give us like an assigned seat for the final, like within the room. I just was wondering if we have that for this class. If not, that's not a problem. I was just wondering if we did.
I want to say no, but I'm not 100% sure. In any case, it shouldn't.
Wait, it shouldn't matter. I was
Yeah.
just asking, yeah.
Yeah. So bring your ID, of course,
Okay.
because we'll have that scanner thingy
Okay.
to scan your ID. So if you have your digital ID, you might have to put your phone on the desk for a bit, and then once we scan it, you can put it away. And then the cheat sheet and your calculators if you want. That's pretty much it. Yeah, I would suggest writing the exam with pencils, because they're easier to erase, because if you make any mistakes, but depends on how confident you are. If you feel like pens are okay, that's fine. Yes.
So there be any questions on like
Sorry, could you speak?
so there be any questions on like
Are there questions about
they're on the practice that I don't practice final, but can they be on the
Yes, all the topics that we have covered can potentially be on the final.
Okay. No, I'm just wondering if it's focus can be on like attitude or everything we've done before. Like can this one be on the
No, yeah, it's all the topics which, like, I cannot tell you which topics to ignore or focus on. I think I mentioned a couple of them. So, the ethics stuff and interpretability you will not be tested on. Mostly I think because interpretability lecture was me explaining a paper, so I don't expect you to be able to reproduce that or like build on that in the exam. But other than that, I think whatever is covered in the course can potentially be on the exam. It's not that the reason I'm talking more about PCA and DataBoost is because that was asked. So, but that doesn't mean that these are the only topics that you need to focus on. Or the VC dimension stuff. Everything we covered. Yes? Okay, if there's nothing else we can adjourn. Thank you so much for the course. I had a lot of fun.